This is Lecture 9 Review by Variate Regression. Consider the following hypothesis. As the percentage of people in a U.S. state who frequently attend religious services increases, the percentage of the people in the state that identifies as pro-life increases. In this hypothesis, the dependent variable is percent pro-life, and the independent variable is percent religious attendance. Variations in religious attendance lead to variations in pro-life. Now, we could collect data on the percentage of people in a state that are pro-life and the percentage of people in a state that frequently attend religious services. And we could put this data on a scatter plot. If we did that, since percent pro-life is our dependent variable, we would put that on the y-axis. And because percent religious attendance is the independent variable, we would put that on the x-axis, and then we would plot the points. And this is what it could look like. So here on the x-axis, we have percent frequently attend religious services, the independent variable, and here on the y-axis, we have the dependent variable percent public pro-life. And I included all of the data points on this graph. And as you can see, it does look like there's a positive relationship between these two variables. So as the percentage of people who frequently attend religious services increases, the percent of the people in the public who identify as pro-life increases. Now, while it does look like there's a positive relationship here, we don't know what the exact relationship is. In addition, we don't know if this relationship is statistically different from 0. So what we can do is run a regression that will allow us to know what the specific relationship is between these two variables and whether this relationship is statistically different from 0. So what regression does is it literally puts a line to the middle of all the points and calculates the equation for that line. This is what the structure of a regression equation line looks like. Y hat equals B hat times X plus A hat. Y hat is the dependent variable. The hat is there is because it's telling us that it's the estimate of the dependent variable. So this line here is just the estimate of percent public pro-life. B hat is the coefficient or slope. That's how steep this line is here and whether it's going in a positive or negative direction. X is just the independent variable, and A hat is the constant or y-intercept. It's where the regression line will cross the y-axis when the independent variable is 0, somewhere down here. To run a regression in SPSS, click Analyze, Regression, Linear. You want to put the dependent variable in the dependent box and the independent variable in the independent box. So my independent variable was a 10, so I'm going to put that in the independent box. And my dependent variable was pro-life, so I'm going to put that in the dependent box. And click OK. And here is your regression output, right here. This chart here shows you how to read the output. So the first row here tells you all the information that you need for A hat, the constant. So this number here is A hat, and this is the sig value for A hat, which I'll talk to you about later. And then this second row here gives you all the information for your independent variable. So this is B hat here, and this is the sig value for B hat. So using that information, you can write out the regression equation. It'll be dependent variable hat equals B hat times the independent variable plus A hat. So we know our dependent variable is pro-life, so I would write pro-life hat equals Then I had to find out what b hat is, and that's 0.804. So I put that there, 0.804 times attendance, because that's the independent variable, plus a hat, and I just have to look here for that, and that's 9.348. So 9.348. So this here is the regression equation. Now, you can also create a scatter plot in SPSS with a bivariate regression line in it, and I'm going to show you how to do that now. So, you click Graphs, Legacy Dialogues, Scatter Dot. You click Simple Scatter and click Define. Then what you want to do is put the dependent variable in the y-axis box and the independent variable in the x-axis box. So attend was my independent variable, so I'm going to put it in the x-axis box. And then pro-life was the dependent variable, so I'm going to put it in the y-axis box, and then click OK. And the graph should pop up in the viewer window. And if you just double left click on it, this chart editor will pop up. You can click out of here because you will not need that. Now to get the line in here, you just click on this box right here. It says Add Fit Line at Total. Then another box is going to pop up. Just close it and then click out of here. And now your regression line is in the middle of the points. Now I'm going to show you how to interpret all of this information. The first step is writing your hypotheses. You will have two hypotheses, the null and alternative. The null hypothesis just says that there's no relationship between your independent and dependent variables. If there was no relationship between those variables, the coefficient b hat or slope would be equal to 0. So your null hypothesis is h subscript 0 colon b hat is equal to 0. Now, of course, based on your original hypothesis or your theoretical expectations, you do expect there to be a relationship between the independent and dependent variables. If you expect there to be a positive relationship, as in as the independent variable increases, the dependent variable increases, then you expect that coefficient or slope to be greater than 0 or positive. So to write that out, it would be h subscript 1 colon b hat is greater than 0. If you expect there to be a negative relationship between the independent and dependent variables, as in, as the independent variable increases, the dependent variable decreases, then you expect there to be a negative slope, or a slope that's less than 0. To write that out, you write h subscript 1 colon b hat is less than 0. So going back to our example from earlier in the lecture, the hypothesis was, as the percentage of people in a U.S. state who frequently attend religious services increases, the percentage of the people in the state that identifies as pro-life increases. This is a positive effect. So my null hypothesis would be h subscript 0 colon b hat is equal to 0, and my alternative hypothesis will be h subscript 1 colon b hat is greater than 0 for a positive effect. The second step in this process is running the regression in SPSS, which I've already shown you how to do. The third step is to write out the regression equation. Once again, it's dependent variable hat equals b hat times the independent variable plus a hat. So we know that pro-life is our dependent variable, so pro-life hat equals b hat, which is, once again, in this box here in the second row, 0.804. So 0.804 times the independent variable, which we know is attend, plus a hat, which is in this box here in the first row, 9.348, plus 9.348. The next step is determining if the coefficient or b hat is significant and different from 0. If b hat is not statistically different from 0, there is no evidence that the independent variable influences the dependent variable. If b hat is different from 0, the independent variable has an effect on the dependent variable. It's either positive or negative. So the first thing you need to do to determine if the coefficient is significant is look at the sign of the coefficient. Is it in the right direction? Is it positive and you expect it to be positive, negative and you expected it to be negative, or is it in the opposite direction than you expected? If it is in the correct direction, then you move on to the significance test, and if not, you do not have significant results, and then you should see step 5B later in the lecture. So going back to our example, we expected there to be a positive relationship, and if we look at the coefficient here, this is a positive number, positive 0.804. So it's in the correct direction, so we should move to the sig test. And this is the sig test. What we're going to do is we're going to look at the sig value here in the second row here for the coefficient. So here it's 0.000. If it's less than 0.002, then the coefficient is significant at the 0.001 level. If not, move on. If it's less than 0.02, it's significant at the 0.01 level. If not, move on. If it's less than 0.10, it's significant at the 0.05 level. If not, then it's insignificant. So this is 0.000. Our coefficient is significant at the 0.001 level, since 0.000 is less than 0.002. So, our coefficient is significant at the 0.001 level. Since the sign is correct, it is positive, 0.804, and 0.000 is less than 0.002. Now, because we have significant results, we should move on to step 5A. If we did not, once again, we would move on to step 5B. Now, if you have a significant coefficient, you can interpret the coefficient. You start by saying something like this. I reject the null hypothesis that the coefficient is equal to 0. The results suggest that there's a significant relationship between the independent and dependent variables. And then you would note if that relationship is positive or negative. It's positive if the coefficient b hat is positive, and it's negative if the coefficient b hat is negative. You would also note the significance level, 0.001, 0.01, or 0.05. And then you could also say, as the independent variable increases by 1 unit, the dependent variable increases if it's a positive effect, or decreases if it's a negative effect, by the value of the coefficient b hat. So, I know that this is positive, and that's what I expected, and I know it's significant at the 0.001 level. So this is how I can interpret this information. I reject the null hypothesis that the coefficient is equal to 0. The results suggest that there's a significant relationship between the independent and dependent variables. There's a positive relationship between attend and pro-life. This relationship is significant at the 0.001 level. As the percentage of people in a U.S. state who frequently attend religious services increases by 1, the percentage of the people in the state that identifies as pro-life increases by 0.804, which is b hat. Now I want to make one last point. This is the last thing you're going to do when you interpret the coefficient. You will say as the independent variable increases by 1 unit, the dependent variable increases or decreases by the value of the coefficient b hat. If it increases because it's positive, you don't have to do anything to b hat to interpret it. But if b hat is negative, what you're going to do is you're going to write decreases, and then you're not actually going to put the negative sign in front of the b hat. So let's say it's negative 1. What you're going to say, it decreases by 1. The reason why you're not going to put the negative here is because you're already saying decreases here. So you don't have to put the negative value there. The next step is interpreting A hat. Interpreting A hat is different than interpreting B hat, so please keep that in mind. The first thing you do when you're interpreting A hat is look at the sig value for A hat, and remember that's always in this box here in the first row. In our example, the sig value is 0.006. What you do is you take that value and compare it to these. If it's less than 0.001, it's significant at the 0.001 level. If not, move on. If it's less than 0.01, it's significant at the 0.01 level. If not, move on. If it's less than 0.05, it's significant at the 0.05 level. If not, then it's insignificant. So looking at our example, we have 0.006. 0.006 is not less than 0.001, but is less than 0.01. So we could say that our intercept is significant at the 0.01 level. We can also note that it is positive because this is a positive value. So we would say the intercept is positive and significant at the 0.01 level because 0.006 is less than 0.01 and it is also positive. You may be able to interpret the intercept A hat if it is significantly different from 0. The intercept tells us the value of the dependent variable when the independent variable is 0. So for example, here is our regression equation from earlier. Pro-life hat equals 0.804 times a 10 plus 9.348. So what if we gave a 10 a value of 0? If we did that, this would just drop out and all we would be left with is the intercept, 9.348. So what we could say is, when a 10 is 0, pro-life is 9.348. But is this really realistic? Not really, because it is unlikely that there is a U.S. state with 0% of the population that frequently attends religious services. So we really can't interpret a 10 this way. Now, if you have an insignificant intercept or A hat, you can't make any conclusions about what the value of the intercept is, so you just don't interpret it at all. Next, you can calculate estimates of the dependent variable for each observation using the regression equation. You should only do this if the coefficient is significant. So basically what you do is you write out your equation and you just insert the value of the independent variable and calculate. So for example, this is our regression equation from earlier. Pro-life hat equals 0.804 times a 10 plus 9.348. So let's say I want to make an estimate of pro-life when a 10 equals 50. So I write out my equation and I just put 50 where a 10 is. And I do the math and it turns out that it is 49.548. So basically what I would say is when 50% of the people in a state attend religious services frequently, then about 49.548% of the people in a state will identify as pro-life. You can also calculate estimate errors. That's just the difference between the estimates and the actual values of the dependent variable. So the estimate error is the actual value of the dependent variable minus the estimated value of the dependent variable. So let's go back to our previous example. So let's say there was a state where 50% of the people in the state attended religious services frequently. And based on this information, we estimate that 49.548% of the people in that state should identify as pro-life. Well, let's say that actually in that specific state, 75% of people identified as pro-life. So this is the actual value of pro-life, and this is the estimated value of pro-life. To figure out the error, we just take this value and subtract this value from it. So 75 minus 49.548 equals 25.452. The last thing you need to know about regression is the R-squared. The R-squared tells us how much of the variation in the independent variable explains the variation in the dependent variable. The R-squared ranges from 0 to 1. 1 means that the independent variable perfectly estimates the dependent variable, while 0 means that the independent variable cannot estimate the dependent variable well at all. So in SPSS, this is what it'll look like when it calculates the R squared and the adjusted R squared. This is the R squared box. This is the adjusted R squared box. This is the value of the R squared. This is the value of the adjusted R squared. To interpret the R squared, you want to make it a percentage, so you take the value. So in this case, we have 0.670, and you just move the decimal place over 2 spaces. And that turns it into a percent, 67%. And basically what you say is variation in the independent variable explains the R squared percent variation in the dependent variable. So going back to our example from earlier, the independent variable was attend, and the dependent variable was per life. So we can say variation in percent attend explains 67% of the variation in percent pro life in a state. The adjusted R squared just takes the R squared and takes into account the number of observations and the number of independent variables. This is the calculation here if you want to know how it's calculated. Basically, it's weighing the R squared by the number of observations you have and also the number of independent variables. Now, in this class, we're only running regressions with one independent variable, but you can add more, and if you're taking Polls 398 next semester, you'll learn how to do that. And what it's looking at is how many observations you have versus how many independent variables you have. If you only have a few observations but a lot of independent variables, then the R squared gets adjusted down a lot. So you really want a lot of observations when you're running a regression. To interpret this, it's similar to the R squared. So you take the number, here it's 0.663, you move the decimal place over twice and it turns it into a percentage, so we have 66.3%. And then you say, after taking into account the sample size and the number of independent variables, variation in the independent variable explains the adjusted R squared percent variation of the dependent variable. And remember that in our example, the independent variable was attend and the dependent variable was pro-life. So we can say, after taking into account sample size and the number of independent variables, variation in percent attend explains 66.3% of the variation in percent pro-life in a state.